on surface states and protects carriers from backscattering is similar for all of these three families, with obvious differences because some of them are insulators, some are metals, etc. So this is the family, and there are more of these materials discovered as we speak. And so that's the setting. Now the properties of these materials, like I said, very diverse. But overall, one can say that they have, there is a number of properties that distinguish them from three-dimensional materials. And this is most clearly seen in the case of graphene, which is the best studied of all these materials. Graphene is atomically thin, and it's a conductor. It's a very good conductor with high mobility. At the same time, it's almost fully transparent and flexible, and electrons in it are strongly coupled to light, and they absorb light in a wide range of wavelengths. And so that obviously also the fact that states are fully exposed, and so one can bring gates very close, and using gates change carrier density. So that makes this material, other materials in a single layer family appealing for various applications. Also it leads to interesting physical properties. They can host topological currents, and they have additional degrees of freedom valleys that can be used to encode information, and so on and so forth. There's a very active research going on graphene and also all these other materials, and it's a huge area that we cannot cover. But I just want to give one slide with this list and say that before we get there, say that there are interesting physics phenomena, some of which we will talk about. Also, because of these unique properties, it's considered of high interest and promise for technology, right? So the properties that I will try to focus on are related with relativistic quantum mechanics that one can model in graphene. And so this is a quick introduction to that. We'll talk about it in more detail next time when we'll get into that. Stuff more closely. So graphene, discovered by these two people, is a hexagonal structure, and the unit cell in the structure is two atoms. And because unit cell is two atoms, you have to describe graphene by a two-band model. So it's different from what we usually learn in solid state physics, when we take square lattice and tight binding model with nearest neighbor hopping, and then we get single sheet bands isolated from each other. So in graphene it's different, and there is a symmetry reason for that. Symmetry reason is that the unit cell is two atoms, and these two atoms are related by symmetry but inequivalent from translation point of view. So you can perform an inversion relative to mid-edge, and then red becomes blue, and vice versa. So they're equivalent, but not equivalent under translations. Because of that, there is a symmetry constraint on the bands in this material, and you get two bands because you have two atoms in the unit cell by simple counting of degrees of freedom. But also these bands have to be connected. And they have to be connected at symmetry points, and these connections called Dirac points are protected by the symmetry. If you take band structure linearized near these points, you'll get actually the band structure should be here. It disappeared. Interesting. So there is a band structure that I put there, but somehow projector didn't like it. So the band structure looks something like a dome. Oh, that's with one band out here. Sorry, one band out here, and the other band over here, and this is the Fermi level. So all these states of field, these are empty, and the symmetry points are where these Dirac points live. If you take this and linearize, zoom in, you'll get these Dirac cones. Disappeared from my computer too. Interesting. All right. So what does that mean? If we're interested in low energy states, and low energy means human scale, because this width, the bandwidth, is about 12 eV. So if we're interested at energies up to, let's say, 10,000 Kelvin, which is about 1 eV, then we have to linearize, and then our band structure with very good approximation is described by a massless Dirac equation. And the Hamiltonian for that is written here. Sigma is a vector made of Pauli matrices. P is two-dimensional momentum. And Pauli matrices are 2x2 matrices. In this case, having no relation with physical spin, they label pseudospin. So they label wave function amplitude on the blue and red side. Okay, and so in the pseudospin space we have 2x2 massless Dirac Hamiltonian. If you compare it with the ordinary Dirac Hamiltonian that you learn about in relativistic quantum mechanics, which looks like this. These are 4x4 matrices that form Dirac algebra. Then you can see that this differs from that. Well, after relabeling, differs from that by mass being zero. And indeed, there is no mass gap separating Dirac negative energy states, positrons from or antiparticles from particles which are at positive energies. So it's massless from high energy physics point of view, or gapless from condensed matter physics point of view, instead of the speed of light, which is here. There is Dirac Fermi velocity, which is 300 times smaller value. So it's an interesting case of particles which behave like massless Dirac particles, which is what we get for Dirac equation in the very high energy limit, when energy is much greater than mc squared. But at the same time, the velocity is very slow compared to the speed of light, right? So that's what we have on graphene. Please ask questions, because we should. I mean, if you want, slow me down or just have fun, ask questions. Yes.
What do you mean by ultra relativistic?
Yeah. So ultra relativistic means that it's like this equation, but in the limit when p is much greater than mc, right? So you don't have to, you can get this limit in the canonical Dirac equation model. Just go to very high momenta, very high energies, and then you can approximate it by dropping mass term, right? And then your 4x4 matrices factor in 2x2 matrices, and you get exactly what this is, because the two valleys that we have here become separate chirality states. Yeah, sorry.
Maybe you have already answered this. So, the absence of mass is the reason why, in the relativistic case, I need to use 4x4 matrices, and here.
That's right. That's right. Yeah, you can't. Without mass term, we can satisfy the commutation relations by 2x2 matrices, and with mass term, as Dirac discovered, you have to use 4x4 matrices instead of 2x2 Pauli matrices. Yeah. So the same procedure is used factor Schrödinger Hamiltonian leads to 4x4 matrices with mass term and 2x2 without mass term.
It's a naive question. Like in transport quantities, how does VF come in? In general, in any band structure, what is actually moving at C over 300? If I
So it's quasi-particles. So quasi-particles move at this velocity, and so if you apply some excitation, then particles excited by this excitation will move at this velocity. And so this actually sets, it's a good question, this velocity sets the limit on how fast graphene can respond to physical signals, or how fast it can transmit physical signals. Because particles individually can only do it at this velocity. You have to use some collective modes, plasmons or something like that, to transmit excitations faster. But if you rely on individual particles, then that's the speed. Or if you take a graphene and magnetic field, then there will be cyclotron orbits, and particles going over cyclotron orbits will be traveling at the speed. The speed is not super high, it's not super low. It's a water velocity with which electron moves in a hydrogen atom, which is of order, which is this scale. So this, up to a factor of 2 is the same velocity. Yeah.
Sorry, going back to the point about 2x2 versus 4x4 matrices, it's also relevant to say that since we just have 2 space dimensions here, that allows you to do things even if you have a mass.
Oh yeah, sure, right. Sorry. Right, but we'll do it one more time next time. Right. Okay. So I'm trying to do it very quickly because I want to get to something else. But I wanted to start from relativistic quantum mechanics and say that already at this level you can draw some conclusions which are important and practically relevant. You see that the linear dispersion that you get is quite steep, much steeper than, let's say, quadratic dispersion in a semiconductor, and so that has important practical consequences. Because of the steep dispersion relation, you can gate graphene very efficiently. You can apply a fairly small gate voltage and change carrier concentration by a little bit. And that moves Fermi energy up and down in a wide range. So you can very easily gate it over one electron volt, 1 or 2 electron volt energy range, and that is orders of magnitude better than what you can do with semiconductors, and it has practical implications. There are many devices existing already that use that. And similarly, steep dispersion leads to other practically important properties, in particular very slow electron lattice cooling, and that makes graphene an interesting playground for strong hot carrier effects. The reason electron lattice cooling is slow is that because of the steep electron dispersion, there is a very large mismatch between electron velocity and phonon velocity in the temperature range where cooling is due to acoustic phonons. Basically, acoustic phonons become very, very inefficient, and then electrons can be easily overheated and remain hot for a long time, and that also is now being explored practically. Then also looking at this Hamiltonian, you can notice that what it says is that pseudo spin and velocity are locked in parallel to each other, and so that if you ask what the consequences of that, you can show that this behavior suppresses backscattering. If you consider scattering on some scalar potential, then this locking will suppress backscattering, something that high energy physicists knew a long time ago and called Klein tunneling, which is the phenomenon that if you take this ultra relativistic limit in the Dirac equation, then every potential barrier becomes transparent. right? But for graphene, you don't have to go to very high energies, and this already, it means that already on a human scale, carriers in graphene are very immune to disorder and have high mobility, and the reason graphene is such a nice material is to a large extent due to this property. Then also, graphene band structure, as we'll talk about today, has Berry phase, and so because of that, graphene can be thought of as a modest, material for various topological materials. One can use it to design topological bands, topological currents, and this has not yet been explored, even on the level of fundamental physics, and no applications based on that. So this is why I chose to talk about it today. Then also because of slow velocity that we mentioned here, if you take fine structure constant will be 300 times greater than for quantum electrodynamics and will be of order 1. That means that in graphene interaction is strong, and from that point of view, it's an interesting material because it's very easy to get new many-body effects. Yeah. Yes, right. So this is for potential disorder, scalar potential. Yeah. But that also happens to be the most important one because they, unless you work very hard, the main source of scattering are some Coulomb impurities, so it's a long-range scattering that is dominated by scalar potential. The electrons don't care about sublattice structure of impurity, etc. So in that case, electrons are protected. Right. So I just wanted to flash, the graphene, as I already mentioned, is a material that is considered of high interest for applications, and there are already some device concepts developed of integrated circuits and photodetectors and broadband modulators, which actually, some of I think this and that, and to some extent this, rely on relativistic quantum mechanics properties that we introduced. So here the broadband arises because of what we said, the ability to gate graphene in a wide range. And similarly here, you can create PN junctions which are so high energy that you can get optical emission by applying a DC current, and you get a green light. Graphene PN junctions and LED. Okay, but I don't want to get into this. I just wanted to say that it's out there. So the topics that I'm going to cover, they are kind of centered around the relativistic quantum mechanics, and I also try to correlate with other lectures. So this is the order in which it will go. Today I want to talk about Berry's phase and how graphene can be used to produce topological currents and use them to study Valley transport. And so then next time we'll talk in more depth about relativistic quantum mechanics and graphene Lorentz symmetry and how it can be used, to study interesting transport phenomena, also connection to the quantum gravity, the Unruh effect, some fun stuff. Then, continuing on that, we'll talk about symmetries and how they can break spontaneously or anomalously, talk about chiral anomaly and quantum Hall effect and scale anomaly and atomic collapse. And this will be the end of the single particle block. Then, up to here we'll be using single particle model, and then after that, talk about interactions, various topics that have to do with interactions. Okay, yeah.
So you keep saying relativistic quantum mechanics, but the key is just the gapless dispersion relation. It seems
of course.
There are other things in relative, there's no Lorentz invariance. I mean, yeah.
Well, there will be no Lorentz invariance today, but there will be Lorentz invariance tomorrow. So just wait.
Okay. But can you be more specific about what aspects of relativistic quantum mechanics are realized, in graphene, and what? Yeah,
So, can we just?
Sure. Okay.
Yeah. But you know, quick answer is many.
Okay.
So Klein tunneling is already demonstrated. We'll talk about it. And Dirac-Landau levels are very different from Schrödinger-Landau levels, and there is relativity built in them because Dirac-Landau levels show clearly that Dirac Hamiltonian is a square root of Schrödinger Hamiltonian, and that it's manifest in graphene quantum Hall effect. We'll talk about that. And so this is well known, but then there are things which are less well known, which is Lorentz symmetry, and you know these other more exotic things, which I'll discuss precisely because they're not well known.
Is it fair to say that all ties back to the gapless dispersion in the band structure?
No. If you take graphene bilayer, for example, then it will be what people call quadratic Dirac Hamiltonian. It's gapless, but it doesn't have Lorentz symmetry. And this one does. So, I'm not saying that one is more interesting than the other. They're all interesting. But if our starting point is Dirac equation for good or for bad, then it's interesting to view it from that point of view. All right. So, good. So, Berry phase, topological currents, and early transport. Great. So, so now I'm going to talk about something that is close to my heart and something that we've been doing over last year. And it's a story that relies particularly on the fact that graphene is a single-layer material in which electronic states are fully exposed, so one can perturb the Dirac Hamiltonian very easily by an external perturbation if it's properly designed, and using that one can create band structures with topological properties. So we'll talk about that. Now, if you succeeded in doing so, let me just start from not from the question but from the answer. Then this is what you get. If you open a textbook, then on solid state physics, then they say that quasi-particles in crystal basically behave the same way as particles. They have energy dispersion, which is somewhat different from particle in vacuum. They have the same charge. They have momentum, which is defined modulo the reciprocal lattice momentum, according to Bloch theorem. And then the equations of motion can be written as Lorentz force equation for momentum and the group velocity for dispersion relation for velocity. However, what's interesting is that some materials particles in some materials also have vorticity. It's an additional ingredient arising because of Berry's phase, and we'll discuss it now. And if particle has that vorticity called Berry's curvature, Berry's vorticity, or Berry's flux, vorticity may be a good word for the moment. Then the equations of motion are modified in this interesting way. There's something like a Lorentz force that appears in the velocity equation, not in the momentum equation. So this Lorentz-like force is applied in momentum space, not in position space, and this quantity, which is the Berry's curvature and is related with Berry's phase in the way we will describe, is a counterpart to the ordinary magnetic field, and has the same effect in momentum space as magnetic field in position space. The name for this term is anomalous velocity. So this is dying so quickly. So this is the normal velocity, the group velocity derived from dispersion relation, and that is the anomalous velocity term. And the presence of this anomalous velocity term, changes dynamics. This term leads to cyclotron motion, and in the presence of electric field there is drift. So if you have both E and B, you get quantum Hall effect, which microscopically looks like cycling orbits drifting perpendicular to the electric field. And then if you have this term, but let's say no magnetic field for simplicity, then you can understand what's going on by saying that free particle dynamics without this term just says that k dot is equal to electric field, and if you put it in here, you will get velocity component perpendicular to electric field. So there will be transverse velocity component. Trajectories will be straight lines, but at an angle to electric field. Okay, so this means that we can have Hall currents. Yeah, and in graphene there will be opposite directions, different valleys, so we'll have valley transfer. But if you focus on one valley, you have a Hall effect at zero magnetic field, and that's quite interesting. You have charge flow perpendicular to electric field, and so that's our first task is to understand where it comes from, and then talk about how to realize it. Any questions? Okay. I mean, there shouldn't be any questions because this is an answer, not a question. But anyway, so what I would like to start with is remind ourselves about Berry's phase, and Berry's phase is. Oops, what's going on here? Yeah. So Berry's phase is something that emerges in the context of a diabatic theorem proven by Born and Fock, 1928. And so this is what they said. So they say that if you have Hamiltonian which is evolving sufficiently slowly, then evolving quantum state tracks an eigenstate, an instantaneous eigenstate. And this is true provided there is a large enough gap between that instantaneous eigenvalue and the rest of the spectrum at all times during evolution. And in particular, it means that ground state under diabatic evolution evolves into the ground state. Again, provided there is gap separating from excited states, and that was the basis for the understanding of molecular spectrum that emerged from this paper. Very important, respected area. However, for us, what's also important is that this picture is not entirely complete. And Berry pointed out, also some people before him, that this is correct. But in addition, dynamics is affected by a phase which is generated by this evolution. And this Berry phase this phase called Berry's phase, for the lack of better name, is distinct from the dynamical phase that we all know about from solution of stationary Schrödinger equation. So this phase that has to be added to the dynamical phase of an eigenstate is expressed through a vector potential defined in configuration space of the system. This is instantaneous eigenstate depending on some parameter. Can be of any origin, and in our discussion it will mostly be crystal momentum, but it can really be anything. So you have an eigenstate depending on this parameter, and then have to take a derivative with respect to that parameter and make an overlap with the state itself. And this defines a vector potential. You have to take a line integral of this vector potential over the history, over the path that describes evolution, a diabatic evolution in the configuration space. And so this phase, as you can see from this formula, even though it contributes to dynamics, it's geometric because the time dependence is implicit. There is no explicit time dependence here. In other words, the phase only depends on the geometry of the path in configuration space and not on how fast or how slow the system moved along it. And so it's geometric and also independent of choice of the wave function. And more precisely, we'll discuss it now. Right. So, question 2: have you seen derivation of Berry's phase, or if you maybe more precisely, would you like to do it on a blackboard? Yes. Yeah. Okay. All right. So. So let's say we are looking at the solution of a time-dependent Schrödinger equation. And how do we do that? We take eigenstates of H. This is time independent for the moment. Take eigenstates and we can write a solution as an expansion in terms of eigenstates with some amplitudes and we can show that all the dynamics is in the time-dependent phase factors, and then psi n are eigenstates of my Hamiltonian, and then each phase as a function of time is simply energy En times time divided by h bar. Then if we have time-dependent problem, described by some h of t, which is varying, but is varying slowly, we can handle it by introducing instantaneous eigenstates. And instantaneous eigenvalues. So at every instant of time, we solve it, find the basis. It's an orthonormal basis. Right, and we can try the same trick. We can try to expand solution in terms of this basis using the same formula. So I'll use the same formula here, except that now this is not true anymore. I have to use theta n, which is given by an integral of En over time, right? So well known. So if I now take this, if I plug this in here and plug this in my time-dependent Schrödinger equation. So this now is time dependent Schrödinger equation, then applying derivative and using the properties of eigenstates, I can simplify the result and get something like simply taking this, plugging it in here, and dropping things that obviously cancel. And it's convenient to separate things that don't cancel into two parts. Involving time derivative of these amplitudes and time derivatives of states and phase factors. So let me explain. When you put it in, when time derivative falls on the phase factor, you generate, because of this formula, because of this formula, you generate En at the time t, and it cancels with what you get on the right hand side, right? So the only two time dependent things that remain is Cn and psi n, and that's what I have here, right? Now, if I take this, use orthonormality and multiply it by a bra state psi m, then by orthonormality this will become Cm Cm of t, and times the phase factor, and I will move the phase factor to the right, and then on the right side, I will have all these terms, and I will take n equal m out and write it separately. So this is mm. And then here there will be a sum over n which is not equal to m. And here there will be psi m, psi n dot. And then here there will be phase factor ei theta. Actually, these phase factors are important, so let me write them more prominently. Okay, something like that. So the reason I separate it like that is because of these phase factors. For n equal m, the phase factors cancel. So there is no phase factor here. For n not equal to m, phase factors don't cancel. And now from this formula for the phase factor, you see that if n is not equal to m, the phase factor is equal to the energy gap between two levels, n and m, integrated over time. And evolution is going over slowly, so the time is long, and so the phase factor difference oscillates very rapidly. And so in this equation, which is exact, by the way, so far we haven't made any approximations, in this equation we can argue that this term, the second term, because of the phase factors, is very oscillatory, whereas the first term is not. So if I now, it's a first order differential equation, if I now integrate it, then the second term that has fast oscillations gives a much smaller contribution than the first term, and that's point number one. Okay. And so we can drop that. Now, if we only keep the first term, we can instantly derive the standard adiabatic theorem. We can say that let's take time derivative of psi n psi n. And of course, on one hand it's 1, because the states, instantaneous eigenstates, are normalized. On the other hand, if I write it out by chain rule, I will get psi n time derivative plus complex conjugate value, which means that the thing here is pure imaginary. So this equation it's for m here, Cm. This overlap, because of that, and because of the left-hand side being 0, this is pure imaginary. Because of that, I can say that Cm square modulus doesn't change in time. And so that's the standard, or time independent. Just say that it's the same value as the beginning of the evolution. So the if you started in some adiabatic state, then you stay in that state. The only thing that may change is the phase. But so that brings me to point number 3. The phase, which is the Berry's phase, is what we end up getting. So we can write this relation also in this way, and then phi will be an integral of phi will be an integral of this quantity times I, and I appeared because I factored -1 into I, and one I went here, and the other I will go in the Berry space. So I can write it like this, or I can also write it, I can reparameterize time by using trajectory and configuration space, and also write it as an integral, as a line integral in the configuration space, going from k node to k of t. Okay, so that's, sorry, took some time, but that's the duration of Berry space. Questions? Yeah.
Can you explain your thing again? Why does the term oscillators for two energy states are different if n doesn't equal n?
Yeah. So there are energy levels. There are energy levels which are spaced apart. Because of that, the phase winding. So let's think about this formula for a second. When phase winding is linear in energy, phase increases for each level. It increases linearly with time, but at different slope, with different slopes set by energy. So if I take phase difference, the phase difference will increase as En minus Em times time, and so that will oscillate if En is not equal to M, and will be constant if it is. And these oscillations, by the definition or by the formulation of a diabatic theorem, they are the ones that we should care about, because if you read again what they said, it says that h of t is changing slowly enough. Slowly enough means compared to the scale h bar divided by the level splitting. And that's exactly the frequency of the period of those oscillations. Yeah, more questions? Okay, so right, good. So we're done with this. If so I can now ask what. Yeah, I know. So I can now ask more probing questions. I mean, we have the formula, very nice. We can ask whether this phase is unique, what it depends on, whether it gauge invariant. I can try, for example, to say the following, that these instantaneous eigenstates, they're defined up to a phase, and the phase, in principle, I can satisfy this relation by taking the phase for this changing phase in the instantaneous eigenstate to be an arbitrary function of time, or an arbitrary function of my parameter. And so I can try this gauge transformation, right? If I do this gauge transformation, then A, using our definition, will change by gradient of that. Will change by gradient of that phase, and so A will not be gauge invariant. However, if you take a loop integral, the same way as in E&M, where magnetic vector potential is not gauge invariant, but loop integral is gauge invariant because loop integral of a gradient vanishes. So the Berry's phase on a cyclic evolution that brings the system back to its original state will be gauge invariant. It won't be zero. It may be zero. It doesn't have to be zero. And so this gauge invariant phase on a loop is analogous, in many ways is analogous to magnetic flux, to Aronoff-Bohm flux. And because of that, it's convenient to process it in a similar way. I can write the phase accrued on a cyclic path using Stokes' theorem as an integral of curl of A over a surface with a boundary on my loop. And then curl of A will be like magnetic field, will be pseudo-magnetic field, a Beer's magnetic field. And so it will be, everything you see, including gauge invariance, how gauge invariance, gauge invariance on the loop and how it's related to phase is very analogous to Aronoff-Bohm flux. And so because of that, it's convenient to develop theory in parallel to that. And we'll do it in a second. Before we do that, let me mention one textbook example that I'm sure you've seen, but it's good to mention it anyway. So the simplest case where Beer's phase can be demonstrated is if you take spin 1/2 particle in a time-varying B field, then the canonical version of a diabatic theorem says that projection of spin on time-varying magnetic field, if field is varying slowly, doesn't change in time. So what's going on is that you have magnetic field, you have spin. Spin typically is precessing around this field. And so a diabatic theorem says that if magnetic field evolves, but this evolution is slow compared to spin Larmor precession frequency, then spin will keep precessing about evolving field and will track its direction in such a way that projection of the spin on magnetic field given by the angle between spin and the field will be constant. That's part one of the diabatic theorem. Part two is about the phase. If you compute the phase, it turns out that the phase will have simple geometric meaning. It will be given by a solid angle swept by magnetic field with 1/2 prefactor. So if your magnetic field rotates in the equator plane like that, then the solid angle is 2 pi and the Beer's phase is pi. That means that which is an interesting prediction. And if magnetic field sweeps a smaller solid angle, then the Beer's phase will be smaller. So this, it's a striking prediction. It's been tested a very long time ago and very carefully in many ways. For example, people did, you can read more about it in Sakurai or some other textbook where this is discussed. You can take a beam of spin polarized neutrons and split it into 2 different beams and send one of them through a spiral magnetic field that is strong and rotates slowly along the beam. Then the neutron spins follow it as neutrons fly through the magnetic field, and then you can bring the beams together on the screen and interfere them and see that if you change the angle of the magnetic field in the spiral, changing the solid angle, then we see a shift of fringes in magnetic field, and that's very clear and beautiful. Any questions here? All right, maybe speed up. All right, right. So if we move on to solids, then in solids a natural configuration space is provided by Bloch momentum or by quasi-momentum. And so just as a reminder, momentum is defined in a lattice Brillouin zone, which is the unit cell in the reciprocal space. And for each value of quasi-momentum in reciprocal space, I can construct a Bloch state, which is a product of a plane wave and periodic function. And so that's the Bloch theorem statement. I can also see that if I vary k, and if I'm in a situation when bands that I get are separate, when the gaps between bands are not closing, then if I vary k, I can define a state on a continuous path in the Brillouin zone, and associate Berry's phase with that path by doing just what we did and specializing to that case of Bloch quasi-momentum, and then using that I can evaluate the phase. This phase will become gauge invariant if I follow a loop. So, for example, if I take, a Brillouin zone is like a torus in momentum space because the k's which are different by reciprocal lattice, one of the reciprocal lattice vectors should be glued together. And so if I make a path which is a cycle on a torus and compute an integral of A over that path, then it will give me Berry's phase, which is gauge invariant, and it will be a property of the band structure. And it may be non-trivial. This phase is known as Zach phase and can be analyzed from the symmetry point of view, can also be measured, and people did experiments recently measuring it using cold atoms. And then also one can ask what happens if I try to, rather than taking one-dimensional path, what happens if I take a two-dimensional manifold in my reciprocal space, or if I have a two-dimensional system, then the Brillouin zone is two-dimensional, so it's this two-dimensional torus, and I can simply take an integral of my pseudo-magnetic field over that area and see what kind of number, what kind of value I get. Well, of course, it will be gauge invariant, but also interestingly, it will be quantized, and one can show that by the integral of Berry's curvature, this pseudo-magnetic field, one gets an integer number known as first Chern class. And it's a topological invariant of the band structure, and maybe zero or non-zero, and this leads. So an analysis of that leads to interesting physical consequences. And I think let me just mention several. So before going to topological bands, let me stop here, and because we built up enough material to be able to derive equations of motion. So I stated at the beginning that there is this new term, pseudo-Lorentz force or velocity, anomalous velocity term, and we can now derive it. Okay, and so. The way there are many ways you can derive it, and this is probably the shortest way. I will be lying you a little bit here, but not too much. So I think it's acceptable for our current situation. So what I can do to derive classical dynamics, I can write down an effective action, and for electromagnetic vector potential, what I'm going to do, I'm going to do the same for Berry's vector potential. I'll write an effective action that that has canonical form, p times time derivative of coordinate, momentum times velocity minus the Hamiltonian, and then add electromagnetic vector potential to it in the form of a times v, right? And I can do the same thing with Berry's phase, writing it a times p dot, with p is momentum, and if I have a more general configuration space which is not Bloch, which is not labeled by Bloch momentum, I can easily generalize that. But for Bloch momentum, this is what we'll write, and then the Hamiltonian here will be a diabatic Hamiltonian. It will be an instantaneous eigenvalue, or the eigenvalue corresponding to the dispersion of one of the Bloch bands. Plus scalar vector potential, and then if you take the stationary the saddle point action condition and write it in the canonical form, with L being the entire thing in parentheses, Lagrangian, the entire thing in parentheses, then from that it follows by a few lines of calculations. I'll be happy to show you that you get both the canonical Lorentz term and the anomalous velocity term. All right. So that's where. So it comes out basically directly from the analogy that we observed, because Berry's vector potential and electromagnetic vector potential. Okay. So now question to you: Shall we derive it? Yes. Okay. It's very important. All right, so we still see equation number 1. Equation number 2 will be saddle point equation that I'll write derivative of Lagrangian with respect to velocity and derivative with respect to time derivative of q. Difference must be 0. Now q here can be any of these variables, can be a p component or an x component. All right. So let's just compute these things that we see here, and let's maybe start with the case. Let's get the ordinary Lorentz force in this way, right? And then talk about Berry's after. So take the electromagnetic vector potential, then this quantity. Oh yeah, and I want the x equation. No, pardon me. So this equation is interesting. So let me do this equation. So to get this equation where magnetic field will show up, I need to take derivative with respect to x dot xi I dot, and that will come from this term. So this will give me pi. And then here there is no x dot, so I skip that, and here there's no x dot, so only here. So it will be EA. And this is the electromagnetic potential. Then this thing will be coming from here, and also possibly from the coordinate dependence of my electromagnetic potential. So I will have minus d h dxi. Right, and so if you look at H has kinetic energy part and scalar potential part. So kinetic energy doesn't generate any x derivative. Potential energy part will, so it will be d phi dxi, and then this will give me E dxi, and then I'll write it as VA, where V will be a shorthand for x dot. Okay, so now we need to take this put together, and maybe before we put it together, let's do this time derivative. So the time derivative of P plus EA will be the following. So it's time derivative of P, and then the time derivative of A has two parts, because this is time derivative taken along trajectory of the particle. This is the, I'm deriving equations for the particle, and A represents some external position-dependent field. So this time derivative is taken along the particle trajectory, and therefore here I have the time derivative, because A might have been varying in time, but also there is a spatial contribution which is proportional to velocity, and it's the, advective derivative. It says that if I have A varying in space and particles moving through it, then the particle is sampling A on its trajectory, and so even if A is not varying in time explicitly, but is varying in space, there will be a contribution to time derivative coming from that, right? And so that's that. So now I have to take this, combine with that, and see what happens. So if I do that, and I will move all the terms with A on the right-hand side, and combine time derivative and potential spatial derivative, and then this term and that term. Yeah. Okay, so what you see here is nothing but electric field ith component, because electric field, if you remember your E&M, it's a negative gradient scalar potential minus Faraday term, the dA dt. So this is the full expression for electric field. Now this you can transform into a double cross product using the vector algebra relationship A cross product with B cross C equal B A in the product with C minus C A in the product with B. And so now you can look at this and compare, and you see that this term is like this term with B associated with grad ith component, and this term is like this term with C associated with A ith component. So then this formula then rewrites as V cross curl of A ith component equal to what we have here, grad I VA minus okay, and so finally this equation gives you a Lorentz force term. Where B is curl of A. Okay, so that's that. And then if you process the other equation in exactly the same way, except you have to switch P and X, then you will get the curl in momentum space of the other vector potential, and that will generate the velocity equation that will generate the velocity equation that will have this instead of gradient of scalar potential, and this instead of Lorentz force. Okay. Any questions? Yeah.
Is there potential time dependent?
There's nothing that prohibits us from considering it. I'm not aware of systems where, well, I guess in optical lattices it could be, because you can vary optical lattice with time. Time dependent, yeah, you can incorporate time dependence easily. Yeah, so you will have to, yeah, you'll get an extra term. Yeah.
Magnetic field is a bare face.
Yeah.
How would I think about electric field?
Yeah, so if it's time dependent, you do just the same thing, and perhaps you'll get an extra term in this equation. So here I was a bit sloppy. You see, I wrote gradient of electrostatic potential without writing Faraday term, thinking about static situation, and so that calculation of blackboard shows how to generalize it for dynamical magnetic vector potential. You can generalize it similarly for dynamical Barry's potential. There's no problem. I mean, this term will survive. There'll be maybe an extra term, but it's not going to cause any trouble.
If their potential is time independent here, then
right.
Why don't they just throw away the term as a full time derivative?
Very good. So the full time derivative is not taken relative to time proper. It's taken over trajectory of the particle. So trajectory of the particle, even if it's moving in a position-dependent but time-independent field, will generate time dependence. So that's how Lorentz force arises. If we throw away this time derivative, our triad will not get the cross product in the Lorentz force. It's important. I mean.
Yeah, but the usual vector potential is time.
Usual vector potential? No, Aaron or bomb solenoid? No. I mean, static magnet. But it can be either. I'm not saying it's limited to static case. It's completely general, easy to incorporate time dependence. It's no problem. Yeah. Maybe I'm missing some. Yeah.
There's something which looks a bit intriguing is that in your treatment, it seems that X and P are treated really on similar footing.
That's right.
But physically, I know that if I switch on a large magnetic field,
yeah.
I can induce some breakdown. So the system doesn't stay in a single band, whereas by definition, I have the impression that there's no breakdown associated to the very phase term. So,
yeah, perhaps, because
the symmetry between X and P has to disappear when you work with very large external fields. So
it's an interesting point. This is actually why I'm doing it in this way. I want to exhibit this symmetry and duality between X and P equations, because I think it's interesting to think about and discuss. Right? I agree that when we are thinking about single particle problems, then the net flux that Barry phase can generate is at most pi over 2, and the next flux that magnetic field can generate can be anything, right? Because of that, for static problems, this term nominally is much stronger than that term, and so the symmetry in the equations doesn't translate fully in the symmetry in the dynamics, but on the formal level it does, and I think it's interesting to observe that. Yeah. So let's see. Oh my God, it's almost. Yeah. So okay. So I'm not going to get into. Sorry, there was another question.
Yes, I have a double question. First thing, I don't really understand what is X, because if we have block waves, they have no position.
For Bloch wave, there is no.
Block waves are delocalized,
That's right.
So I don't really understand what is the x variable position.
Oh yeah, no, I told you I'm lying, right? Right. So this is one of the places where I'm lying. There is also another one. So thanks for pointing it out. But if you do it more carefully, same answer, extra 10 minutes. But yeah, no, yeah. So the usual answer to this is that if you have a quasi-particle, then you describe it by wave packet. So it's the same discussion as for group velocity. When we talk about wave group velocity, then to explain what this velocity is, we have to introduce wave packets and think about center of masses or guiding centers for these wave packets and how they move, and then it turns out that they move as if the whole wave packet, over some time, moves with that velocity. And so the same approach can be used for electronic waves. Although I think for electronic waves, it's not as restrictive as for other waves, because there's also Fermi surface constraint, and so there are wave packets are naturally kept sharp by the Fermi surface. So it's not as dangerous as for ordinary waves to do this. Right. So let me maybe finish with this. So there are mechanical analogs for these equations of motion that various phenomena based on Magnus force. And as you know, if you have a ball spinning and the air is moving around it, then there will be a lift force pointing from the region where velocity is low, local velocity is low, and pressure is high to the side where local velocity is high and pressure is low, and it's called Magnus lift force. And it has various manifestations. You can play curveball when you play tennis or when you play baseball. And so the point for this is that the reason I'm talking about this is that I'm trying to say that what we're dealing with here is more generic than electrons under some strange crystal. Any object that has vorticity and we're trying to move it, you don't need to apply magnetic field. Just vorticity and motion will generate something like Lorentz force, and you can demonstrate it very easily by rolling something down a plane with and without vorticity. I need to let me try this. So this will be my first experiment. Okay, so this will fall down there, right? And then the paper cylinder that builds up vorticity as it rolls down will curve back, right? So you see that goes there and this goes here. So there's clearly something that curves it in, right? Yeah. So this worked a little better. Right. So I think we started 10 minutes late, but so let's see. What's the plan? Do you want to start 10:30, or are we having break, or what? How much time I got?
In principle, we have 10 more minutes.
Yeah.
So today the coffee break is a little bit shorter. So if you have 10 more minutes, then we can start. We start anyway at 11 o'clock.
Yeah. Okay. So let me say that.
If you want to stop now.
Yeah. No. I want to say that I will say it quickly because I think Joel will be saying much of the same. There will be some overlap with what Joel will be saying. So what I want to say now is just make the point that this anomalous velocity and Berry's curvature that we discussed and its impact on transport of quasi-particles in Bloch bands has many different manifestations, and there is a whole area of physics inspired by geometry, and the first example historically known is the integer quantum Hall effect, which can be where the quantization of conductivity, physical observable, can be interpreted by relating it with the quantization of the chair number. And then more recently, topological insulators appeared where, again, you have an insulator, and then, if you are at the energies where some bands are filled and other bands are empty, and your field bands have a non-trivial Chern class, then you get various anomalous properties, topologically protected H states and transport along them that I'm sure you will hear from Joel. My interest is slightly different. I'm interested in band transport, not in the edge transport. So I'm interested in the situation when you have a band which is partially filled, and there is a number of these cases known. For example, where anomalous velocity is important. For example, there is a phenomenon which is as old as the conventional Hall effect, going back to 1881, and it's called anomalous Hall effect. And it says that it discovered by Hall, the same person who discovered the Hall effect. So there are two Hall effects that he discovered. But anomalous Hall effect shouldn't be confused with the conventional Hall effect. And the observation was that even if you turn off magnetic field, if your metal is magnetic, you still get a Hall effect, which may or may not have been surprising to Edwin Hall, but it should be surprising to us because we know that there is no, the coupling in magnet is via spin, so there is no orbital coupling. Maybe there is a little bit of it, but it doesn't, so small that it doesn't explain any of those observations. Nevertheless, there are many materials which are, when they are in a magnetic state, they show very strong Hall effect, and that Hall effect has been discussed over years, and there's a painful history associated with it. But recently, people started converging on the point that it has something to do with Berry's phase and transport, anomalous transport related to it. There's also the spin Hall effect, where the story is very similar, and there are several contributions to it due to scattering and disorder, but also there is an intrinsic contribution which arises directly from the equations that we wrote. And then what I am going to be interested in is in the same realm. Graphene band and Valley currents in it, and I want to, I will show you a situation when graphene can be used to form a band with non-trivial topological currents, and they can be observed experimentally, and this has been done a few months ago, so we'll talk about it tomorrow. As a preparation to it, let me just say, can go for maybe 2 or 3 more minutes. As a preparation to it, let me say the following. If you would like to use graphene as a topological material, you have to show that it has Berry phase, and this Berry's phase vector potential has non-trivial curvature. So in principle, graphene has a potential for it, because if you take pristine graphene, which is described by massless Dirac fermions, then you can think about massless Dirac fermion Hamiltonian that we wrote before as a Zeeman Hamiltonian in the field. In the effective magnetic field, you can write it as sigma times B effective, and this B effective is pointing along momentum. So this looks like spin 1/2 Hamiltonian and magnetic field, which is pointing in different directions in K-space. And so it obviously has Berry's curvature. However, if you compute it, you can write down explicit eigenfunctions. and from them, plugging them in this formula, you will see that the solid angle, in the solid angle picture, that the Berry space is equal to the solid angle divided by half, we always get, for any trajectory in momentum space, we always get a fixed number, which is either pi or 0, depending on whether our trajectory encloses or doesn't enclose the Dirac point. So the Berry space is there, but Berry's curvature is singular. It's 0 everywhere except Dirac point, and then it's a delta function at the Dirac point. So it's not having any interesting effect. And this is same thing in more length with showing where Berry's vector potential is pointing. Let me skip that. We'll come back to it tomorrow. Let me do this. Maybe that will be the last slide. So if you have, the situation changes, and it has been pointed out a few years ago by New and collaborators. Situation changes if you have a perturbation that breaks A-B sublattice symmetry in graphene. And that perturbation, it opens band gap in graphene, so it's no longer a massless Dirac particle, but a massive Dirac particle, and the mass is related to the size of the band gap. And B also, as soon as that happens, in that picture you get a Z component of magnetic field, so you get something like delta sigma 3. So your B is no longer in the XY plane; it has a Z component, and because it has Z component, you can get an arbitrary solid angle depending on the loop you go around. So you get Berry's curvature, which has a smooth and non-trivial distribution in K-space being peaked. For each of these bands, it will be peaked near the Dirac point, and will form pockets of positive and negative Berry's curvature above and below the gap. And so what we would like to do is to realize this in experiment and show that we can create topological bands of this type, and then send carriers and see that we can play the curveball. Okay, so that's where we'll start tomorrow. All right, good. So we. Oh, questions? We got 1 minute for questions. Yeah.
So you were telling us about the abelian Berry
That's right.
phase, where you have a non-degenerate eigenstate.
Yeah.
And you can also think of the non-abelian
Yes.
Berry phase, where you have some degenerate subspace, and you look at the adiabatic transport of that, I think along a closed loop. I'm wondering, it seems that in systems where you have line nodes or point nodes, you can't think of a Chern number for an individual band there. It isn't well defined. But is it possible to try to define something like a Chern number in that case, where you sometimes have a degenerate subspace and sometimes don't? And then move on to thinking of like the anomalous Hall conductivity in terms of a Chern number, but where you only consider contributions from the Berry curvature, below the chemical potential.
Yeah, it's an interesting question. So I think in the experiment, in this example that I will talk about tomorrow, in the experiments, non-abelian regime may be there's no obvious way I can think of that could be accessed, but let me think about it some more and see if we can come up with something. Yeah. Okay, coffee break.
But you can do it today. Yeah, you know the entrance to the building that we normally go in?
Yeah.
Just to the left, there's a room where they have all that stuff. If you have enough adapters as well, so you actually rent outlets.